Okay, well, thank you very much all for coming. As announced, these are going to be lectures about the minimal model program. Now, I'm a little bit embarrassed to give these talks here because there's the audience is very varied. So there's some senior people like Matsuki who have known about the minimal model program for a long, long time. And so some of what I'll say will be very well known to them. But I was also told that there are young students in the audience, so I'll try to make it accessible, especially at first. I would like to start with the first lecture being mostly an introductory lecture. So what are my goals in this series of lectures? I would like to give an introduction. Maybe I should write them down. So I'd like to start by giving an introduction. So what is the minimal model program? And I'd like to explain in some detail how one runs a minimal model program and what the main results that the minimal model program builds upon. So probably at some point I will, for example, prove some of the sort of more classical result. For example, I think I'll prove the base point free theorem, which is a key ingredient in the proof of the cone theorem, and illustrates quite well some of the methods and techniques of the minimal model program. And then I would like to talk about more recent developments in the minimal model program. So I hope to actually finish by giving you a fairly complete proof of the existence of flips theorem. Which really includes some of the most recent results and is somewhat technical, but hopefully I can break the proof down into simple enough steps that you can get a good feel for it. So this is sort of my general plan to start slowly with an introduction, talk about some of the main classical results of the minimal model program, and in the end give the proof, so hopefully a complete proof of the existence of flips of some of the most recent exciting results. I'm going to have some notes. I'll put the notes online on my webpage. I haven't done that yet. I hope to figure out how to do it today. So there should be some notes online, which will include pretty much everything I say here, plus a little extra, including a few exercises. And at some point, hopefully, I'll put some references. The notes that I plan to put up today online will not be the complete notes for the whole course. I will have to revisit them several times, and no doubt I'll find many typos. If you find typos, please let me know. And if you have questions, please don't hesitate to ask during the lecture, or you can come to my office before lecture or after lecture to ask me about more details. So I believe my office number, well, I have my key, so I should check. My office number is 351. So don't hesitate to come and ask for questions or other references or things like that. Okay, so any questions before we get started? Okay, so let's sort of get started with a gentle introduction to what is the minimal model program. Well, for the purposes of these lectures, I'm going to be considering complex projective varieties. So I will forget to mention the complex numbers very soon, but let me at least mention it once. So these are always over the complex numbers. And such a variety is just defined as the zero set of a bunch of polynomial equations, homogeneous polynomial equations. So it's an algebraic variety. These are homogeneous polynomials in the variables x0 through xn. So your typical example is one homogeneous polynomial of degree d will define codimension subvariety of the corresponding projective space. Okay, so the goal of the minimal model program, so we want to study these up to birational isomorphism. So two varieties, x and x prime are birational if and only if, well, there's several equivalent definitions. So one definition is if they have the same field of rational functions, or equivalently of meromorphic functions. But maybe a more hands-on equivalent way of saying that two varieties are birational is if they have isomorphic open subset. So if and only if there exists open subsets in the Zariski topology, of course, such that U is actually isomorphic to U prime, right? So the rational functions are determined by the values on an open subset. Okay, so that's what birational varieties are. And at least psychologically, while in practice, it's very useful to recall that by Hironaka's theorem, given any variety x, is always birational to a smooth variety to some x prime, which is smooth. Another smooth complex projective variety, and so that's a complex manifold. Okay, so at least at the beginning, we'll focus our attention mostly on smooth manifolds, on smooth varieties, because we, after all, would like to classify these objects up to birational isomorphism. So let's assume that the dimension over the complex numbers, I won't write that, of x is d. Then the next thing I should tell you is what is the canonical line bundle, because that's what we typically use to classify a variety. So the canonical line bundle is just the top exterior power of the cotangent bundle, of the dual to the tangent bundle, right? So I'm assuming that x is smooth, then the tangent bundle is a nice vector bundle. You take the top exterior power and you get a line bundle. So locally, we can look for sections. Let's say S would be a section on some open set U of the nth tensor power of the canonical line bundle. Then locally, S looks just like a holomorphic function times dx1 wedge dxd. So these would be x1 through xd would be local coordinates. Then this differential generates a canonical line bundle, and then you can take the corresponding mth tensor power. Okay, so I guess the first question is, why bother considering line bundles at all? Well, if you're trying to study the geometry of something, usually you need to do it in terms of functions on that object. And since this is a compact complex manifold, global holomorphic functions are going to be constant, so they won't be very useful. So in order to pick some interesting finite dimensional space of functions, we can look for global sections of a line bundle. And the only natural line bundle that we can come up with is what's called the canonical line bundle. I guess that's why it's called canonical. And of course, all of its tensor powers. So this is pretty much the only natural line bundle to consider. And so it's natural to consider sections of this line bundle. And if you're lucky, they won't necessarily be constant. And in fact, this is going to play a fundamental role for us. So what can you do with section of the canonical line bundle, or of tensor powers of the canonical line bundle? Well, first of all, you could, so you could consider, let's say, S0 through Sn, a basis of global holomorphic sections of the corresponding tensor power. And then this will define for you a map to projective space, a rational map to corresponding projective space. Just by sending a point x, you just evaluate these sections. And that gives you a point in projective space. This map is not everywhere defined. It's not defined on what we call the base locus. So this is not defined on the base locus of omega x to the tensor m. So the base locus is a set of points x and x with the property that S of x is equal to 0 for every section, for every global section of this tensor part of the canonical line bundle. Okay, so this is called, maybe I should put an index M underneath. This is called the nth pluricanonical map. It plays a very important role in studying the birational geometry. And maybe another thing I should mention is the canonical ring. So the canonical ring is just the graded ring where each graded piece corresponds to sections of the corresponding tensor power of the canonical line bundle, right? So if you have a form of degree m and a form of degree m prime, and you multiply them together, you get a form of degree m times m prime. Okay, so one thing that I should mention immediately is that this is a birational invariant. Maybe I'll say a few words later about why it's a birational invariant. And maybe it's quite complicated, so you can extract from this birational invariant some other, some interesting numbers. So for example, you can think of the quadratic dimension of x to be the transcendency degree of this ring over the complex numbers, of course, -1. And it has several other equivalent characterizations. So you could also think of this as, so as defined here, this will be an integer which can be either -1, 0, 1, all the way up to d, where d is the dimension of x. Another way of thinking of the quadratic dimension is the maximum dimension of the image of x via these pluricanonical maps. Maximum of the set of all dimensions. Okay, so essentially, the quadratic dimension measures the rate of growth of sections of tensor powers of the canonical line bundle. Right? So another way to think of it is h0 of omega x is equal to, let's just say, approximately a constant times x to the m. So then this will be an m to the power quadratic dimension of x. Okay? So if you think of the sort of corresponding Hilbert polynomial, it's just the degree of that Hilbert polynomial. Okay, so that's what the canonical ring, well, the canonical ring is, and it's going to play a very important role in what follows. Any questions so far? Okay, so what's the easiest possible kind of birational equivalence? So typical example of birational equivalence, you could have z contained in x, where both of these are smooth, so a smooth subvariety of a variety. And then what you can do is you can blow up x along z, and this operation replaces z by an exceptional divisor, which is just a projectivization of the normal bundle in x to z. And in fact, it turns out that birational equivalence is generated by operations like this. And it's very easy to check that when we do this operation, then the canonical ring is unchanged. So how would one see that? Well, we need to be able to compare the canonical line bundle of these two varieties. So let's say that C is equal to the codimension in x of z, right? Then the normal bundle to z and x will be a bundle of fiber dimension c. So in fact, this e to z is a bundle whose fibers are projective spaces of dimension c minus 1. And an easy local computation will allow you to relate the canonical bundle of X prime with, maybe I should, it's easier to write it still in. So the canonical bundle of X prime will, let's denote this map by F, will correspond to the pullback of the canonical bundle on X, where now you can allow poles on the exceptional divisor to order. Okay, so now it's always easy for me to make a mistake along these lines, so I believe it's to order C minus 2. Let's just do a quick sanity check. So if you take X prime to be the blow up at a point at the origin, say, of C2, so then the canonical bundle of X prime is the pullback of the canonical bundle of C2 plus one copy of the exceptional divisor. So it looks like I have my formula wrong. Got carried away. So it's C minus 1. And of course, if you blow up a smooth point on Cn, then you'll get the difference between the canonical bundles will be n minus 1 times the exceptional divisor. So in this and many other computations, one of the ways to check it is by using the junction formula, which we'll do several times in what follows. So maybe let me not do it right now, but let me just observe then that sections, let me use now additive notation instead of multiplicative notation. So kx denotes a divisor corresponding to a meromorphic section of the canonical line bundle. So sections of this guy correspond to sections of the pullback of m kx plus m times e, where the key point is that this is effective, but it's also exceptional divisor. And so by the projection formula, adding an effective and exceptional divisor does not actually change the number of sections. So that is easy to see that this is the same as the number of sections of the canonical line, of the corresponding tensor power of the canonical line bundle on X. So that shows you that the canonical ring is a birational invariant, at least under blowing up a smooth subvariety, and then, clearly under the equivalence relation generated by this procedure. Okay. So what's the goal of the minimal model program? So what the minimal model program does is the following. So the minimal model program, you start with X smooth. So by Hironaka's theorem, you can always pick a smooth projective birational model, and then we perform a finite sequence of hopefully well understood elementary operation, which are called flips and divisorial contraction of flips plus divisorial contractions. So X, maybe I'll denote that by X0, X1, X2, all the way until we get, let's say, XM. And then we want that the output, so there should be two possibilities for the output. The first possibility should be is either a minimal model. So what does minimal model mean? That means that the canonical class is Nef. I guess this is shorthand for eventually numerically effective, but what it means is that the intersection with any curve is always non-negative for any curve C in X. Okay, so that's one positive outcome. And the other positive outcome is a Mori fiber space. So a Mori fiber space would mean that we have a morphism from X, say, to a variety Z of positive fiber dimension with the property that Kx, the canonical class, is relatively anti-ample. So if I take the negative of the canonical class, the dual line bundle if you prefer, this is ample over Z. So in particular, that tells me that the fibers, let's say F, are what are known as final varieties. So in particular, minus K of F is ample. Okay, so this is, I'm not telling you any of the details right now. We should get that fairly soon. But this is sort of a wish list. We would like to perform these finitely many flips and divisor contractions and either end with a minimal model or a Mori fiber space. And maybe I should make a couple of remarks. So from this point of view, you think of Fanos should be building blocks of the second case of Mori fiber space, of Mori fiber spaces. And, you know, hopefully you can understand the geometry of Fanos really well. And on the other side, hopefully knowing that K of xm is Nef gives you useful geometric information, right? So I should also say these two possibilities are mutually exclusive. So maybe I'll explain it as follows. If Kx is not pseudo-effective, corresponds to the case of a Mori fiber space, and Kx is pseudo-effective, corresponds to the minimal model case. So I realize that I've now introduced a new term, so I should explain what I mean by pseudo-effective. So let's say that D is a Q divisor. Then we say that D is big. Let me write down two possible definitions. So one definition is that the codarial dimension of D, we remember this is the transcendency degree over the complex numbers of the ring associated to divisor D minus 1. So if this is maximal, it's equal to the dimension of D of X. This is also equivalent to saying that we can write this divisor. Let me assume maybe, yes, assume that it's a Q divisor. We can write this divisor as being Q linear equivalent to an ample divisor plus an effective divisor. So A is ample, Q divisor, and E is an effective Q divisor. So that's what a big divisor is. Now, D is pseudo-effective if it is a limit of big divisor. If it's in the closure of the big cone, if it is in the closure of the big cone. So in more practical terms, if you fix any ample divisor A and any epsilon greater than 0, then D plus epsilon A is big. So a typical example of something that's pseudo-effective but itself doesn't have many sections is the following. E.g., take a topologically trivial line bundle with the property that it's P to the tensor M. It's not torsion for every M in Z. Then you see the codaric dimension of D will actually be -1. Because since this is non-torsion, no tensor power of that actually has a section. If you have a topologically trivial line bundle which is torsion, which is not torsion, then no tensor power can have a section. So that tells you that the codaric dimension is -1, as negative as it can be. However, so I'm mixing additive and multiplicative notation. P, it's a topologically trivial line bundle, so it's numerically equivalent to 0. So when I add any multiple of an ample line bundle, it's numerically equivalent to an ample line bundle, and ampleness is a numerical condition. So in fact, this is ample, hence big. So this is an interesting case. So that tells us that this line bundle here is pseudo-effective. That's an interesting.
When you say closure, where are you?
So I have to be in. Did I write closure? No, I didn't write it. Okay. Well, if I wrote it, I'd like to write it on the blackboard. So what you do, you can consider the cone of big divisors. Big divisors. So I'll think of this. Maybe I'll just write it as big of x. This is a cone inside n⁻1 of x. So what do I mean by n⁻1 of x? I mean numerical classes of divisors. So let's think of this. Well, it's a smooth variety, so I don't have to worry if it's Cartier or Weil divisor. So let's think of this as divisors with real coefficients. And I'm going to quotient this by numerical equivalence. So D1 is numerically equivalent to D2 if and only if D1 minus D2 intersect with any curve C is always equal to 0. Okay, so the reason why we like to think about N1 is because it's a finite dimensional vector space, whereas if you consider the space of all divisors with real coefficients, it's clearly infinite dimensional. So this is a more friendly object. And when I write something like this, I'm assuming a non-trivial result that you'll find in Lazarsfeld's book, for example, that being big is a numerical property. If two divisors are numerically equivalent, if one is big, if and only if the other one is big. So writing this down is a non-trivial thing, is a non-trivial statement. OK, and not pseudo-effective are all the other divisors. So D is not pseudo-effective if that doesn't happen. So there exists an epsilon greater than 0 and an ample divisor A such that D plus epsilon A is not big. OK. So one can check. It's not too hard to see. OK, so, well, maybe I should write something down. It's always better when you write something down. So if you have a minimal model, I should try to convince you that if I have a minimal model, that should correspond to the case where the canonical class is pseudo-effective. So if a divisor D, well, let's work with Kx, is Nef, then that tells me that Kx is pseudo-effective. Now, this is really easy because you have to consider Kx plus epsilon ample. And this has nice intersection properties. So for example, when you intersect this with any curve C, this will be greater or equal to epsilon A dot C. And so by one of the criteria for ampleness, that tells you that, in fact, this divisor is ample. So Kx plus epsilon A ample. which implies Kx is pseudo-effective. Okay, so in the case that you have a minimal model, that's why it corresponds to a pseudo-effective divisor. And of course, you would have to check that this property is not destroyed by a finite sequence of flips and divisorial contractions. But I've not told you yet what flips and divisorial contractions are, so I cannot prove that to you yet. And how about the Mori fiber space case? Minus Kx ample over Z. Well, this is sort of an easy exercise to check that this cannot be pseudo-effective, right? So if minus Kx is ample over Z, then that tells you that minus Kx plus epsilon A will be ample over Z for epsilon small enough. The reason is that ampleness is an open condition. So if I perturb it by a small, if I make epsilon sufficiently small, this stays ample over Z. So now I have to check that if this divisor is ample over Z, then Kx plus epsilon A is not big. And this is really, really easy to check. So for example, you could just take sections of minus m Kx plus epsilon A, and you could multiply them by sections of m Kx plus epsilon A to get sections of X, which this is a one-dimensional space. But if I'm assuming that this is ample and this is big, then I have lots of sections in here and lots of sections in here. So this is approximately a constant times m to the dimension of x. This is another constant times m to the dimension of x. So we have a contradiction, right? You could not have these big groups of sections mapping into a one-dimensional space. Right? You know, almost everything would have to be in the kernel, but simple tensors are not in the kernel, for example. Okay, so any questions about the overall very vague goal or this business about pseudo-effective divisors and non-pseudo-effective divisors? Okay, then I'll move on. Okay, so I've talked about the pre-canonical line bundle and the canonical ring. So maybe we should start by making an easy example of the one-dimensional case, which everybody's familiar with, but it's pretty quick to do. So there's no harm in doing it to set the tone for the rest of the lectures. So when the dimension is 1, there are essentially three cases. You have codaric dimension of x equals to -1. So in this case, you only have one possibility. X is the projective line, in which case the canonical line bundle corresponds to homogeneous polynomials of degree -2. And consequently, there are not many interesting homogeneous polynomials of negative degree. So this will be 0 for every m greater than 0. And hence, the canonical ring of omega x is very non-interesting. It's a copy of the constants in degree 0. Okay, so the canonical ring is completely useless when studying curves of genus 0. But on the other hand, so I should say that the genus of x is 0. But on the other hand, curves of genus 0 are very easy, so we can study them with other. There's only one of them, and we understand it very well. The next case is the case of codaric dimension equal to 0, in which case x is isomorphic to, it's an elliptic curve. There is a one-parameter family of these. In affine coordinates, think of, for example, y squared is x minus 1, and x minus s, let's say. So you can think of these curves, of this curve x, when I write it that way, I'm thinking of it as being a degree 2 cover of P1, which is actually branched along over 4 points, 0, 1, infinity, and this point s. And by fixing 0, 1, and infinity, I've sort of fixed the biratio. So s actually gives me non-isomorphic elliptic curves. Now, so elliptic curve, we draw this picture, but it's actually flat, right? It's would be more accurate to think of it as C2 quotiented out by a top-dimensional lattice. And so that's telling you that the tangent bundle of X is the trivial line bundle. And in fact, so in this case, the canonical line bundle is a trivial line bundle. So the canonical ring is going to be, well, in each degree I get holomorphic functions, and global holomorphic functions are constant. So this is going to be isomorphic to C of t. So in other words, I'm using t for each degree. Maybe I should just write it down, h0 of omega x to the tensor m. These are always, in each degree, I get a copy of the constants. So again, the canonical ring is completely useless in studying the geometry. These are already more complicated examples. There's a one-parameter family of them, but you have to find a different way to study them. Well, for example, I've indicated that somehow you can think of all of them as cubics. But the case that is useful is a case where the quadratic dimension of X is 1. In this case, the degree of the canonical line bundle is 2g minus 2. And since g is greater or equal to 2, right, we already took case of elliptic curves have genus 1. Genus 0 and genus 1 have been taken care of. Now we're looking at the case of genus greater or equal to 2. This degree is greater or equal to 2. Specifically, it's greater than 0. So it turns out that omega x is ample. So that means that some tensor power of omega x is very ample. In fact, omega x, the third tensor power, is very ample. I guess you really need the third tensor power for curves of genus 2. For curves of genus greater or equal to 3, the second tensor power will be enough. So the third pluricanonical map actually gives you an embedding from X into the corresponding projective space. And if I get my Riemann-Roch computation right, this is 5g minus 6. And the degree of the image is going to be 6g minus 6, because the degree of the canonical line bundle is 2g minus 2, and I'm taking the third tensor power. OK, so this tells you that if I consider the canonical ring, this is going to be a very interesting ring, because it has lots of sections. It must have lots of sections. It has enough sections in it to actually recover X itself, right? Because the third tensor power embeds X into projective space, right? And so the way that you sort of say this explicitly is that X can be obtained from the canonical ring in a unique way by taking proj of this canonical ring. So writing this, in order to write this, I have to observe that this ring is finitely generated. Right? And so how am I so sure that this ring is finitely generated? Well, you can essentially read it off from here, right? Because when I look at this map, it's telling me that omega x is essentially given by taking homogeneous polynomials of degree 1 under this map here, restricting them to x, right? And so it's not hard to exploit that to actually check that the canonical ring is finitely generated. And there are classical theorems that address this too. It's not a difficult thing to prove. Yes?
Can I be a pain in the ass?
Yes, please.
The previous platform.
Previous one, oh.
Yeah, I'm a little bit uncomfortable with the last argument you said. Number 1.
This one here?
Yeah. Number 1, there are plenty of maps that goes in many sections, tensor many to C. So this is, you're talking about the divisor, so I agree with you. But another place is find us mx plus EA. That's only ample over Z. But you said C and D. These are dimensions.
Okay, yes. So
that's one point. So you like a little bit of modification of the argument.
Okay, so So Kenji is asking me to show a few details of this argument. And I will have to agree with him. The argument is not incorrect, but it is incomplete. So let's see a few of the details that you.
You can tell me to shut up. Shut up.
No, I mean it's. So typically, what happens is that when one person has a question, 3 or 4 other people are thinking of the same question. So maybe I should add a few details. Okay, so where have I cheated a little bit? So the first thing. This argument, you should think of as this argument as corresponding to the case that dimension of z is equal to 0. So then this gadget is honestly ample without being ample over z. So then what I wrote down is correct. But there's still a remaining question is, how am I so sure that the image of this map is non-zero? There is plenty of stuff in the kernel of this map. I can easily write down something in the kernel of this map. No, maybe it's not so easy, but...
No. What I said was, if H0 of nx plus a has lots of sections, its minus has no section.
Right, but somehow you have to prove that, and this is one way to prove it, is because... So in divisor notation, you would have a divisor d plus a divisor g mapping to divisor d plus g, which has to be equal to 0, because divisors linear equivalent to O of x are just the trivial divisor. Okay, but these two divisors are effective, so the only way their sum can be 0 is if each divisor is 0. So that is, I think, fairly convincing. Now, the other question is, why is it so obvious that I can reduce to the dimension z equals 0 case? Well, the idea is to look at fibers. So if I restrict to a fiber, ampleness now over z becomes honest ampleness. And so I have minus a divisor is ample, plus the divisor, if I want to show it's not big, so let's assume that divisor is big. So if you have a divisor that's big, when you restrict it to a general fiber, it stays big. And so the argument I just said goes through verbatim. So it's essentially incomplete, but for the sake of time, I did skip a few steps. And so don't hesitate to ask the questions. Or if you don't want to interrupt the flow of the lecture at some point, but you still want to ask the question, ask me either in the break, after the lecture, or come to my office. It's never a bad time to ask a question. OK, except that now I got distracted. Oh, yes, we were talking about the canonical ring. We were saying that this is interesting. In the case of genus greater or equal to 2, these are also known as general type. Right? Most curves are of this kind, so that's general type. And the canonical ring allows you to recover x with this proj construction. And I was going to tell you, if you're not used to thinking about the proj construction, one way I like to think about it is as given by the generators and relations of this ring. So if you pick generators, then that means essentially that you're thinking of a surjection from a polynomial ring onto this canonical ring. Now, there's a bit of a problem with the grading. Let's assume it's generated in degree 1, which is not the case, but you could pass to a Varieties subalgebra. Let's just assume it's generated in degree 1. Now, then you have, when you take proj, you get a map in the other direction, in this case an embedding. And so then proj of this polynomial ring, this is my projective space, and the equations of x are now given by the relation between these generators viewed as element of the canonical ring. So it's a fairly natural construction. OK, so that was the sort of review of the one-dimensional case. Then let me see what next topic I want to talk about. Oh, yes, I want to talk about the two-dimensional case, of course. So the two-dimensional case is much more interesting. One of the reasons it's much more interesting is that in dimension 1, two curves are birational if and only if they are isomorphic. Two smooth curves I'm still talking about. But in dimension 2, for surfaces, there are surfaces that are birational but not isomorphic. And we've already seen an example. So the example is x prime, which is the blow up at the point P of, let's say, P2. This maps to P2. This map is birational, not an isomorphism. So one way to check that it's not an isomorphism is that the Betti numbers are different, right? So here you're taking a point. P is being replaced by an exceptional curve that's a P1, so a Riemann sphere. So it's changing the second Betti number. The second Betti number increases by 1. We call this a -1 curve. So it has the property, this is just a local computation. E squared is the same as kx intersect with E. This is -1. So it's called the -1 curve. And just for a consistency check, when you do kx plus E and restrict it to E, since this is a smooth curve and a smooth surface, you get the canonical class of E. Now, the degree of this is -2, so the degree of this side better be -2 as well. Kx dot E is giving you -1, and E squared is giving you another -1. So I didn't make a silly mistake this time, okay? So, and in fact, it turns out that if two surfaces are birational in general, if x1 is, maybe I should say x is birational to x prime, then we can get from one to another by a finite sequence of blow-ups followed by a finite sequence of blow-downs. Okay, so you blow up a bunch of points repeatedly on the first, on x, and then you blow up a bunch of points on x prime, maybe a different number, right? Because eventually the Picard numbers have to match. So, you know, this Picard number is bigger than this Picard number. I'll have to blow up more points on this one. But eventually you get isomorphic surfaces. And each step you are introducing a new -1 curve, a new curve with these properties. And what Castelnuovo's criterion says, so suppose that we have a smooth surface that contains a -1 curve. Then this curve is necessarily a rational curve, and it's arising by blowing up a point. So then there exists, let's say, y and a point P on y such that x is just given by blowing up the point P on y. And in fact, this -1 curve is being contracted to the point under this blow-up map. Okay, so that's what Castelnuovo's criterion said, and that's been known probably for over 100 years. So that gives you a way to look at the surface and say for sure that it was obtained from another surface by blowing something up. Okay? So when I look at this diagram that I illustrated, sort of we're trying to get rid of, we're trying to look for a smaller surface, a most elementary surface, a minimal surface. And so we wouldn't pick one that's obtained from another surface via many blow-ups. That seems wasteful. So if anything, we want to find the one that has not been obtained from another surface via blow-ups. So what we do is we start with smooth surface x. If it contains a -1 curve, then we apply Castelnuovo's criterion. Then we have x is equal to the blow-up at a point P of a surface y. And notice that the Picard number of x, if you don't know what the Picard number is, just think of the second Betti number, is equal to the Picard number of y plus 1. So the operation is non-trivial. It's decreasing the second Betti number by 1. Now, what we do is we replace x by y and repeat. So you're starting from a smooth surface. There either are no -1 curves, or there's at least one -1 curve. You blow it down, and you repeat the procedure. Now, since the Picard number is actually a positive integer, this procedure can't go on indefinitely. This procedure terminates. And so we can assume that in one equivalence class, we have what's called a minimal surface. So it terminates with minimal surface. Which, watch out, what this just means is that there are no -1 curves. Right? So previously, I told you a wish list was a minimal model where the canonical class was going to be Neff. I'm not saying that we've already found that canonical model. It could be that a minimal surface in this sense is not actually a minimal model. And this is a problem just coming from tradition with the name. So let me give you an example of a minimal surface which is not a minimal model. Right? So you could take, for example, Hertzberg surface Fn. So this is the projectivization of the rank 2 vector bundle on P1, OP1 direct sum, OP1 plus or minus n doesn't matter. Let's say plus n. Okay, so this is a rank 2 vector bundle. You take the projectivization, you get a P1 bundle over P1. So the fibers are rational curves. And let's assume that n is different from 1 because you see this surface always contains a section, maybe E contained in Fn. It always contains a section of negative self-intersection. E squared is equal to minus n. So if you put n equals 1, you'll have a section, so a rational curve with self-intersection minus 1. That's a -1 curve. And then it wouldn't be minimal. But otherwise, these are actually minimal surfaces. I mean, they have lots of rational curves on them. For example, the fibers are rational curves. But those fibers have self-intersection 0. They're not -1 curves. OK, but this map that I exhibited is a Mori fiber space. Right? So it's not like a dream isn't coming true. Just the old nomenclature is not appropriate with the with the new nomenclature. Right? Now, notice that there's another sort of that Fn is birational to Fm for every n and m, right? So the minimal models are not even unique in this sense. These bad minimal models, which are anyhow Mori fiber spaces, they're not even unique. So you're probably familiar with the following picture. So this is the picture of my Fn. Now, say I take this point here, P, and I blow it up, right? So what do I get? I get this fiber will sort of split as the union of two fibers. When I blow up this fiber, it will have two components. This will now be a -1 curve. But notice that this fiber had self-intersection 0. When I blow up a point, it now has, let me just denote it by F again, it now has self-intersection -1. And so if you stare at it for a second, you realize that the fiber became a -1 curve by blowing up that point. So now I can apply Castellanovo's criterion and blow that down to get a new fiber here. So this fiber here is sort of special because it's been obtained from this one by blowing it down. And there's sort of a special point, that's the image of that. What happens now when I blow down this curve, when I blow down, let's see, my picture is slightly off. There's no special point there. I'm blowing down this fiber. So this one is this minus 1 curve. It becomes the new fiber. And now the self-intersection of this section, let's call this E prime, when I do the self-intersection, so let's assume that this one had self-intersection minus n. So let's think about this a second. When I blow up a point that has nothing to do with the section, the self-intersection is unchanged, minus n. And now I'm blowing down a curve which intersects this fiber. So I believe if I do the computation correctly, this self-intersection will be now n minus 1. So to go back this way, I'm blowing up a point on the section. So the self-intersection will go down by 1. It will become minus n. Yes, it will go down by 1 and become minus n. OK, so this shows you that this is called an elementary transformation. We'll see later that it's an example of a Sarkisov link. I'll explain what those are in probably the third lecture, I imagine. So there's a vast generalization of this to all dimensions, but it gives you non-trivial birational equivalence between two Mori fiber spaces. So even if we don't want to think of these as minimal models, we just want to think of them as Mori fiber spaces, the outcome of the minimal model program is not unique. You start with this guy. If you contract this minus 1 curve, you end with this Mori fiber space. If you contract this minus 1 curve, you end with that Mori fiber space. And they have different invariants, so they cannot be isomorphic. Right? So running the minimal model program can have more than one output, even in dimension 2. OK? But that's fine. That's just the way it is. OK. So that seems like, I don't know, good news or bad news. It's a bit more interesting than maybe you expected if you haven't seen surfaces before. Maybe good news is if the codaric dimension of x is greater or equal to 0, then minimum models, let's say, and x is minimal, then the canonical class is indeed Neff. So it is a minimal model in the sense that I was talking about before. And it is unique. So when the codaric dimension is greater or equal to 0, minimal models are unique. And in fact, what the minimal model does, it sort of removes, or maybe I should say that. So let me try and give you an idea why it's unique. I'm not going to prove it because I think to prove it, I need to know, at least the easy way is to know that the canonical line bundle is semi-ample. So, well, maybe let's state it. So actually, kx Neff implies, OK, now I don't remember what the exact multiple is, that m kx is equal to 0 for some, well, let's be more precise. Let's say the mth tensor power of the canonical line bundle is trivial for some m greater than 0. So for all m sufficiently divisible. Now, you certainly need at least 6 for codaric dimension 0, but you might need higher for codaric dimension 1, and I do not remember. I'm pretty sure that 24. Does anybody remember what the exact multiple we need to get 0? Is it 12 enough?
You mean semi-ample?
No. So, oh my goodness. I was thinking about the codaric dimension 0 case. OK. OK. Let's say that. OK. So then kx is semi-ample. I apologize. I'll get to the statement that I was trying to write down in a second. I need to put a slightly different hypothesis. Kx is semi-ample. So what that means is that m kx is base point free for some m greater than 0. And so what is really going on? So think of it in the following way. You start from x prime, you run your minimal model until you get to x. Now, every time that you do a blow up, right? So remember when you have xi to xi minus 1, this is just getting rid of one of the minus 1 curves, call this fi, then k of xi is equal to the pullback of k of xi minus 1 plus your exceptional divisor, ei. So if I call this map f, then k of x prime is the pullback of k of x plus, let's call it e. This is some effective divisor whose support is the exceptional set of this map. Every time you blow up a point, you're adding the exceptional curve. So support of E is equal to the exceptional set of F. So what's the minimal model doing? It's actually just getting rid of the base loc, the stable base loc of kx prime. So another way to view this is as the stable base locus of kx prime. So the stable base locus of kx prime is just the base locus of m kx prime for m sufficiently big and divisible. Right? Because by the projection formula, E has to be in the base locus, and since this is a semi-ample, some multiple of that, okay, so maybe I can write it, m kx prime is the pullback of m kx. This guy has no base locus plus m e. So from that, you see that the base locus is precisely this m of e. So if you don't want to think about some scheme structure, it's just the support of this m of e. Okay, so what the minimal model does, it contracts down the curves in the base locus. The base locus is uniquely determined by the canonical ring. So that actually tells you that the minimal model is going to be unique, because you know exactly what curves are being contracted. And once you know the curves that are being contracted, you actually know what the output is. You cannot have two different smooth surfaces that are isomorphic. If they're isomorphic in codimension 1, outside of finite many points, then they're actually isomorphic. So that's what's going on with that. So maybe this is a good moment to take a 10-minute break, and then we'll continue. We'll start to explain how the program works in higher dimensions. If you have any questions, you can ask me during the break. Should I get started again? OK, so continuing with the dimension of x equals 2, I'm almost done with that case. So I said that mk of x is base point 3 for some m greater than 0. That actually tells you that by an easy argument that the canonical ring is finitely generated. The reason being that whenever you have something that's base point 3, when you look at the corresponding pluricanonical map, you get a map to projective space, and under this map, omega x to the corresponding tensor power is just a pullback of OPN1, so it's sort of intimately related to homogeneous polynomials of degree 1, and when you consider higher tensor powers of the corresponding tensor power. So it's quite, once you have that the canonical bundle is semi-ample, it's quite easy to check the canonical ring is finitely generated. So now, specializing to the case where the codaric dimension of x is equal to is maximal. So again, in this case, we say x is of general type. Then we can define the canonical model to be given by the generators and relations of the canonical ring. And so what's actually going on is that you run your minimal model program to get to your minimal model, which is unique in the case of positive, non-negative codaric dimension, so certainly in the case of general type. However, this is not necessarily a canonical model. You actually have now a morphism down to the canonical model. And what this morphism does, it contracts curves with the property that they're again rational curves, but now they have the property that E intersect K of X is 0, right? Because if this is Nef, there are no longer any negative curves with respect to the canonical class, but there could be curves that intersect the canonical class 0. So it's enough to get rid of the rational curves that intersect the canonical class 0. Hence, by the junction formula, E squared is actually equal to minus 2. But then the reason why I sort of originally people were not so excited about the canonical model is that it comes with singularities. So this canonical model has mild singularities. They're known, of course, as canonical singularities, or they're known as rational double points, also known as Duval singularities, also known as canonical singularity. So they're very mild. For example, K of X is still a Cartier divisor, but it's not necessarily, it's not smooth. OK, so it's very easy to write down examples of those singularities, and there's no avoiding this. But, sorry, K of X canonical is Cartier. And in fact, of course, it's ample. And in fact, I believe 5 times the canonical class for a surface, 5 times the canonical class is very ample. Remember, for a curve, you just needed 3 times the canonical class, but actually 3 times the canonical class is no longer enough to get a very ample device. OK, so that sort of finishes the story for surfaces, at least the part of the story that I want to mention. And now I would like to move to higher dimensions. And maybe I should start by illustrating that the situation is going to be more complicated. So for surfaces, at least we had this nice feature that minimal models are smooth, but already in dimension 3 or greater, minimal models may not be smooth. Okay, so what's the easiest example? So let's say dimension of x is greater or equal to 3. Minimal models are typically singular. So what's the typical example? So the typical example is you take A to be an abelian threefold. So that's a complex projective torus of dimension 3. And on this abelian threefold, you take the involution, which is generated by the inverse. Right? So this is the map that sends x to minus x. Now, this map, let's just call it sigma. Sigma has, what is it, 2 to the 6 fixed points. In a neighborhood of your fixed point, the map looks like locally, these fixed points look like sigma of x, y, z. Suppose that x, y, and z are local coordinates, appropriately chosen local coordinates in the neighborhood of the fixed point. Then this is just minus x, minus y, minus z. So now, maybe I should give this guy a name. And I should probably keep the name that I have in my notes so that I don't get confused when I look at the next. So I call this V in my notes. And these 2 to the 6 fixed point give rise to singularities, which are isomorphic to a cone over Veronese surface. Veronese is capital, Veronese surface. So the Veronese surface is P2 embedded by quadratic polynomials. So if you look at this, what are the invariant polynomials? You know, x squared, y squared, z squared, xy, xz, yz. So that should convince you that locally the singularity should be a cone over a P2 embedded by the complete linear system of homogeneous polynomials of degree 2, and hence a cone over a Veronese surface. So we can resolve this by blowing up the singular point. And so, so here's V, and here's my singular point, of which I have many. I have 2 to the 6. I can blow up these points to obtain an exceptional divisor E contained in the resolution V prime. And then E will be isomorphic to P2, right? If this is a cone over a copy of P2, then when I blow it up, the exceptional divisor is P2. But now it's important to know that it's you want to know what linear series is embedding the variety over which you're taking a cone. So it's a complete linear series OP2. So in fact, OEE, when I restrict E to itself, I'm going to get OP2 minus 2. Okay, so what I want to do now is I want to compute the differences between the two canonical divisors, the canonical divisor V and the canonical divisor of V prime. So, so I write K of V is equal to, let's denote the map by F, so the pullback of K of V, K V prime. And the difference has to be given by a multiple of the exceptional divisor, because that's the only divisor that is on V prime but is not on V. So, let's denote this. Hopefully it's the same number I use in my notes. Okay, so let's denote by A the number of copies of the exceptional divisors that account for the difference between these two divisors. Note that K of V is not a Cartier divisor, right? Because I have this singularity. And in fact, what's clear is that 2K of V is a Cartier divisor. So this number A should belong to, should have denominator at most 1/2. And in fact, we'll see that it is exactly 1/2, I hope. So how can I figure out what this number is? I can do adjunction, right? Since this E is a smooth surface in a smooth variety V prime, I can compute K of E by doing K of V prime plus E restricted to E. But now, by what I just wrote, you see E is mapping to a point. So the pullback of K of V, since this is a Q Cartier divisor, will be trivial on E. So this will be the same as A plus 1 E restricted to E. Now, the degree of E restricted to E is minus 2. The degree of the canonical class of E, that's the canonical class of P2. So that's minus 3, right? So the canonical class of P2 is O of minus 3. And so, now this linear equation is rather easy to solve. That tells you that A is equal to 1/2, right? Because then I have 3/2 times minus 2 is equal to minus 3. Okay, so what that is, so that's sort of one interesting computation that tells you that the difference of the canonical divisor is not always an integer. But what I claim that this says is this implies that V has no smooth minimal models. And in fact, it has no minimal model where the canonical class is a Cartier divisor. Canonical class has to be has to be 2 times the canonical class will be Cartier, but the canonical class itself will not be Cartier. So why is that? So I have V. Suppose I have another V star. So suppose that this is another minimal model. Well, by the argument that I sort of hinted to before, V and V star, or we'll certainly check it more carefully later, those are isomorphic in codimension 1. Isomorphic in codimension 1. But they don't actually have to be isomorphic. There are plenty of examples where you have more than one minimal model already in dimension 3, even if the codary dimension is greater or equal to 0. OK, but what can you do? You can take a common resolution. So maybe I should say a word about how you get a common resolution. So you use Hironaka's theorem. What you can do is you can take, these are birational, so they're isomorphic on an open subset. You just take the normalization of the graph of the rational map between these two and resolve that. So you get a common resolution of the two. And you denote by P and Q the maps. Then let's think of the gadget P upper star of K of V minus Q upper star of K of V star. I claim that this is 0. Now, why is that? Well, on the one hand, this gadget here is Q nef. This divisor is Q trivial. This divisor K of V is nef, so its pullback is going to be Q nef. Then, by the negativity lemma, this tells me that the difference, P star KV minus Q star KV star, it's an exceptional divisor, which is Q nef, so it has to be less or equal to 0. By the same reasoning, if these are both minimal models, this is also P nef. And by the negativity lemma, this, once again, says that this difference has to be greater or equal to 0, hence it's equal to 0. Okay. So maybe I'll recall the negativity lemma in a second for those of you who do not remember it. But where's the punchline? So the punchline is that the multiplicity along E of the pullback, let's denote, of K of W minus Q upper star of K of V star is the same as the multiplicity along E of K of W minus P upper star of K of V, which I already computed. This minus that, it's 1/2. But you see, if this guy was smooth, or if this class is Cartier, this is smooth, so this class is Cartier, so I'm doing the difference between two integral divisors, I can't get 1/2. That's my contradiction. Right? So this tells me KV star is not Cartier. So what's this negativity lemma that I used? It's a lemma coming from surface theory. So suppose that we have f from x to y, some proper birational morphism, and E, let me do a slightly more general version, E, a divisor with the property that f lower star of E is effective and minus E is f nef, then E is effective. So in this case, I'm applying it to the case where the push forward of E is 0. It's an exceptional divisor. So this is satisfied. I am verifying this condition, P nef on one side, Q nef on the other side, and I'm concluding that E is greater or equal to 0 and less or equal to 0, hence equal to 0. So a corollary to the negativity lemma is if E is exceptional and E is numerically equivalent to 0, then, okay, effective, exception, then E is equal to 0. And maybe I should sort of, the argument that I gave there in general, if x1 and x2 are birational minimum models, then when I take a common resolution, they're isomorphic in codimension 1, and when I take a common resolution, P upper star of k of x1 is always the same as Q upper star of k of x2. So you could have more than one minimal model, but essentially studying the canonical class on one minimal model is the same as studying it on another minimal model. They share many properties. And we'll get more into the detail of that. OK, so for now, the takeaway of this is simply that already for surfaces, singularities are starting to naturally appear. The canonical models have mild singularities. You could say, well, we can get away with minimal models, so let's not worry about that. But for free folds, even the minimal models have to have, you have to allow them to have some mild singularities. Now, this is not a very scary singularity, right? It's a quotient by an involution. And the canonical class is not Cartier, but twice the canonical class is Cartier. As singularities go, it's not scary. It's a rational singularity. It has many nice properties. And in fact, this is going to be true for all singularities that we encounter. So I'm going to check my notes now, but I would imagine that now is the right moment to start talking about what the right category to run the minimal model program in is. And so that will depend on defining the singularities of the minimal model program. So Camerota log terminal, log canonical, canonical, and terminal. So let me start by defining what a pair is. So we're going to talk about pair. So what do I want? I want X has to be normal, particularly reduced and irreducible variety of dimension D. And B will be a sum of bi. So these bi's are typically rational, but possibly real coefficients. So let's allow them to be real coefficients right from the beginning. And when I write it this way, bi's will denote prime divisors. Now, the key thing here is that we're going to insist that kx plus b is R Cartier. So by R Cartier, what that means, it means that it's equal to a sum of di, where the di are Cartier divisors, and the little di's are real numbers, positive or negative. OK. Typically, if I allow bi to be less than 0, I will talk about a subpair. More often than not, when I talk about a pair, I like to assume that the bi's are greater or equal to 0. OK, so now how do I define my singularities? Well, life would be a lot easier if x was smooth and b was simple normal crossings. So let's just reduce to that case. So let's let f from x prime to x is going to be a log resolution. So you have to be slightly careful with log resolutions. You really want to insist, otherwise you can run into trouble, that the exceptional set of f is a divisor.
So when you say pair, if the coefficients are non-negative?
No. But when I allow them to be negative, I will try to emphasize it by saying subpair. Oh. And often, I will assume that the coefficients are non-negative, and I'll forget to say that they're non-negative. I'll just say it's a pair. And people do this all the time. So I'm not even sure what exactly the right notation is.
But when you say pair, it's not assumed.
No, it's not assumed. When I say Camerota log terminal pair or log canonical pair and so on, it is assumed that the coefficients are non-negative. And if I'm talking about KLT pair with possibly negative coefficients, I really should say a sub-KLT pair. That's sort of the correct usage, I believe, but you know, everybody does things slightly different just to keep us on our toes. Okay, so we're trying to give the definition of various kinds of singularities. So what I'm going to do now is I'm going to compare the canonical class of x prime and the canonical class of x. So I pull back kx plus b. I'm allowed to do this because this is an R-Cartier divisor. That's why it's so important to insist that it's an R-Cartier divisor. If it's an R-Cartier divisor up to this formal linear combination, it's really a bunch of Cartier divisors. Cartier divisors are locally defined by rational functions. I just pull back those rational functions. No problem there. Okay, and let me write this as kx prime plus b prime. So this equation defines b prime. Okay, so here are the various flavors of singularities. We say that, oh, I didn't finish telling you what local resolution is. I need the exceptional set to be a divisor. I need x prime to be smooth. Otherwise, what kind of resolution is it? And I need the exceptional set of f plus the strict transform of b to have simple normal crossings. So it's going to be a union of irreducible smooth divisors intersecting as transversely as possible. You know, in local coordinates, they look like hyperplanes intersecting transversely. Okay, so I write this equation that defines b prime. So xb is KLT, respectively, or if and only if the coefficients of b prime are lesser or equal, but not equal, so strictly less than 1. Log canonical, if and only if the coefficients are lesser or equal to 1. Okay, so in particular, it's clear that KLT implies log canonical, but not necessarily vice versa. Then I will say that xb is canonical or terminal if and only if the coefficients of b prime with respect to some divisor e, let's do it this way, of b prime minus the strict transform of b. So canonical less or equal to 0, and terminal is going to be strictly less but not equal to 0. Okay, so typically for canonical terminal singularities, we think of having empty boundary, in which case I'm saying that the whole of b prime is less or equal to 0, or the whole of b prime is strictly less than 0. Okay, so these are new classes of singularities. So it would be nice to experiment a bit and to have some clue as to what they look like. But let me give you one more definition before I give some examples. So I'll denote by A, E of x, B. This is the discrepancy. This is going to be minus the multiplicity along E of this divisor B prime. So let's do our first computation. So when I have, let's say Cn, or any smooth n-dimensional variety, and I blow up a point, a smooth point, so in this case the origin of Cn, what I get is that, call this x, well, let's call it x prime and this x. Then I get that k of x prime is, as we wrote down before, the pullback of k of x plus n minus 1 times the exceptional divisor. So a of e x 0 in this case is actually equal to minus n minus 1. So that's the computation of that discrepancy. Now, I should say it's easy to see, but not completely obvious, that smooth varieties satisfy all of these conditions. They are, in fact, terminal. Smooth varieties are terminal. OK, what's a more interesting example? We could take x to be a cone over a curve. Well, that's going to be a singularity. So what kind of singularity do we get? So there's one I guess the most basic case to compute is, let's say that we're doing the cone. C is going to be a rational curve. So this is P1 of degree, let's say, n. OK, so how do you can resolve this by blowing up the vertex, let's call V the vertex, to get another, to get a resolution. You'll get a smooth surface. You'll have an exceptional curve E with the property that this exceptional curve is, of course, a copy of P1. The normal bundle will have degree minus n, so E squared will be equal to minus n. And now we can try and compute, this is a log resolution, so we can use that to compute if this singularity is KLT, log canonical, canonical terminal. OK, so let's see how the computation goes. I don't know. So this was x. This is x prime. Let's say that this map is f. So we'll write that k x prime is equal to the pullback of k of x plus a times the exceptional divisor. So now we need to figure out what this multiplicity a is. But I've already introduced a strategy to do that. It's to use a junction. So k of P1 is isomorphic to k of E, which is just k of x prime plus E restricted to E. You know, after all this is a smooth curve and a smooth surface. And so now, from this equality, k of x prime is the pullback of k of x, which restricted to E is trivial, plus AE. So this becomes, just like before, A plus 1 E restricted to E. So this is minus A plus 1 times N. And this is 2. And of course, I'm keeping my fingers crossed that I don't do a calculation mistake, because whenever on the blackboard, I always do a calculation mistake. OK, so I'm trying to solve for A. So A plus 1 is
minus 2.
Well, I did warn you, right? OK, so A plus 1 is 2 over n. So A plus 1 is 2. So it looks like the discrepancy. Please take a minute to check my computation. I think I got that right. So in other words, maybe the better way to write this equality is that k of x prime plus 1 minus 2 over n E is equal to the pullback of k of x. When the singularity was like smooth or terminal, you were expecting to get a contribution on this side. But now we're getting a contribution on that side. This tells us really that the ring of k of x and the ring of k of x prime are not isomorphic. In order to make them isomorphic, you need to introduce this boundary. OK, so let's look at this list. So this singularity is log canonical, sure, because this number is, in fact, strictly less than 1, so it's even KLT. But it's not canonical or terminal. OK, so that's an example of something that is Camerota terminal, but not canonical. In fact, surfaces, terminal surfaces are the same as smooth surfaces. So since we knew we had the singularity, we knew that couldn't happen. And canonical are these rational double points, these Duval singularities. This is not a Duval singularity. Maybe I should flesh out this example a little bit more because it will be useful for something called a junction that we will need later on. So there's this map. Yes?
For your definition, maybe you want to say quantifier. Is that for all long resolution or for some?
Well, I'm sleeping it under the rug a little bit. So for these, you have to check this for 1 or equivalently any log resolution. So either way, you check it on one resolution, then it automatically holds on all other log resolutions. For these ones here, you're supposed to check all log resolutions.
Another thing is, from your definition, it's not clear canonical implies Kelty, but it is true, I think.
There may be some stupid restriction that you need to make. So, for example, dimension better be greater or equal to 2. Because in dimension 1, according to this definition, the coefficients don't even have to be less or equal to 1, or something stupid like that.
But I think it does imply.
Yeah, so once you exclude all the trivial stupid cases, then log canonical, the other way around, canonical implies KLT, terminal always implies canonical. Here there's some stupid cases like one-dimensional cases where it's not the case. Okay, so here we have one interesting class of examples. I just wanted to now make compute for you what a junction does for a smooth divisor on a singular surface, because we'll certainly need something like that later on. So let's let L is this line here, and let's try and compute what is k of x plus L restricted to L. Well, under this resolution map, if I look at the strict transform, let's call it L prime of L, it's actually isomorphic to L. So I'm actually going to do the computation on L prime. So this is the same as the pullback of kx plus L restricted to L prime. Okay, so let's compute this. Now, we've already computed. The reason I'm doing it now is I know what the pullback, I'm calling it, I should just call it F, not new. I've already computed what the pullback of kx is. The pullback of kx, here it is. It's this mess here. So let me write that in. Kx prime plus 1 minus 2 over n e. And now I need the pullback of L. So pullback of L will be L prime plus 1 over n e. Because L goes through the vertex. It's not actually a Cartier divisor, right? If you intersect x with a hyperplane, you get n different copies of L, right? So now when you pull that back, you'll get one copy of the exceptional divisor. So you get 1 over n copies of the exceptional divisor for each line. Or another way to check it is intersect this with the exceptional curve E. You get 1 from here, you get 1 over n minus n, so you get minus 1 from here, it cancels out. L prime plus 1 over n e dot e is 1 minus n over n equals to 0. And this convinces you that L prime plus 1 over n e is the pullback of L. So this formula is correct. I restrict this to E. OK, so what do I get? Well, I get a little bit confused. Sorry, not to E, to L prime. OK, so I get a little bit confused. But kx prime plus L prime, so this guy and this guy is going to give me k of P1. But then what do I get here? I get plus 1 minus 1 minus 2 over n plus 1 over n. So 1 minus 1 over n let me denote by V. So prime will be this point here. Right, this was the point V, so the intersection, this V prime lies over V. It's the intersection between the exceptional divisor and L prime. So I have my answer. When I do a junction in the singular case, the ambient variety is singular, kx plus L restricted to L is not going to be K of L, right? So you can think of this as K of L. There's a correction term, 1 minus 1 over n V. This thing here is known as the different. So technically, what should I write? Different in L of x comma 0. That's the technical notation. So later on, I'll tell you what the exact formula is in general, but we have already computed the formula that I'll use at a certain point in one interesting case. Any questions about this computation?
Sorry, but for your log resolution, you assume exceptional divisor exceptional locus is a divisor.
Yes.
And exceptional f plus f inverse of these essence. Under these conditions, I believe those canonical terminal conditions is also for 1 or equivalently all. If I'm wrong,
no, I don't. So okay. So let me give an example where I think. Okay, let's debate the following example.
Sorry.
No problem. So let's consider the following pair. C2, and I pick 2 lines from the origin, and I pick them with coefficients 2/3 and 2/3. I claim that this is KLT, but not canonical. KLT, not canonical. Why is it KLT? Well, of course, that's already a log smooth situation. It's a simple number crossing divisor. I don't have to take any resolution to check it. However, if I blow up the vertex, I'm going to get the following. I'm going to get an exceptional divisor, E, and the strict transform. These will appear with coefficients 2/3 and 2/3, and this will appear now with coefficient 1/3. In other words, it's easy to do the computation. The pullback of kx plus 2/3 L1 plus 2/3 L2 is equal to kx prime plus 1/3 the exceptional divisor plus 2/3 the strict transform of L1, which I denote by L1 again, and the same thing for the strict transform of L2.
You're right.
But that's fine. That's this time. But that, there's no harm in working out a few examples. So now let me write down a somewhat disappointing example. So you can do a similar computation with a cone over an elliptic curve. And you do the same exact computation. Actually, it's slightly easier, but I won't get into why. So if x is cone over elliptic curve, then it should be the case that I take the resolution x prime to x, f, then k of x prime plus e with coefficient 1 is the pullback of k of x. Well, I can check it very easily, right? Because 0 is the degree of the canonical class of my elliptic curve, which should be the degree of kx prime plus e restricted to e, which should be the degree of f upper star of kx restricted to e. Oh, wait a second. The pullback of e maps to a point, so this pullback is 0. The degree of 0 is 0. I was right. OK, so this tells you that this is a singularity which is log canonical, not KLT. OK, so I believe if you want to write down a surface singularity which is canonical but not terminal, you just do C2 modulo x, y goes to minus x minus y. right? I think that's a canonical but not KLT singularity. Right, note that the canonical class here will be Cartier, right? Because dx wedge dy is dx goes to minus dx wedge minus dy, which is again dx wedge dy, so it's actually canonical. So yeah, so I think I got it right. Okay, so I think we've now seen examples of singularities that are of all three kinds. And why did I say that this example was going to be slightly disappointing? It's not a rational singularity. However, there's a theorem. Okay, there's several versions of this theorem. I forget who the version I'm going to write is due to, but it sort of dates back to work of L.1. If xb is KLT, then x has rational singularities. So I won't prove this. I'll prove some similar results. The proof of this, there's an easy proof in Kolar-Mori's book, which just uses Kawamata feedback banishing. But what does having rational singularities mean? So over the complex numbers in characteristic 0, so for a resolution, f from x prime to x resolution, then we have f lower star of O x prime is isomorphic to O of x. So this is the derived push forward. So what this formula means, it just means f lower star of O x prime is O of x. Well, that's obvious. This is just the fact that x has normal singularities is normal. But the content is that Ri f lower star of O x prime is equal to 0 for every I greater than 0. So in particular, if you look at homology groups Hj of Ox prime, they are always isomorphic to Hj of O of x. And so what this is telling you is from the cohomological point of view, KLT singularities are very easy to work with. They're essentially just as easy as smooth varieties.
Can I ask a question?
Sure.
When you say that XB is KLT, do you assume some condition coefficients of B?
Yes. So, so maybe I should say here, for all of these definitions, I'm assuming that B, let me just write it somewhere. KLT, LC, canonical, terminal assumes B greater or equal to 0. Otherwise, I should say, I'm sure I'll forget, we say sub KLT, sub log canonical, blah, blah, blah. And certainly, if I just assume sub KLT, that's going to fail, because essentially what I can do is I can take my cone over an elliptic curve, take some divisors through the vertex with negative coefficient. So when I pull it back, it's going to decrease the coefficient of the exception divisor to be less than 1. So sub KLT.
So the coefficient might be possibly larger than 1?
If you have sub KLT, so okay, so let me work it out in this example here of the cone over
coefficient of B prime less than 1 implies the coefficient of B.
But now if I add something with negative coefficient here, it's going to make this coefficient slightly smaller, hence less than 1. So in some sense, this singularity is sub KLT, sub log canonical. In fact, sub KLT, but it's still not rational. You know, you're just pretending it's rational by making some coefficient negative for no reason. So it really, one should always think of this condition. The problem with thinking of this condition is that in my definition, well, not my definition, but in the definition, when I do this pullback, this thing here is now a sub pair. right? Even when you take P2 and you blow up 1 point, you'll get coefficient -1 along the exceptional divisor. It's not something we should be scared of, but yeah. So that's something that you usually just don't worry about initially. Okay, so I was trying to say that these singularities are rational, they're nice, they're Cohen-Macaulay, so really cohomologically they're very well behaved. Makes life very easy. Okay, so maybe I should emphasize again, we've kind of done this, but emphasize now that if we work in the canonical or terminal world, then the canonical rings are unchanged.
Chris, I think like a large consensus question, but are you assuming coefficient of B to be smaller than or equal? But that's a consequence.
Oh, was that your question?
Yeah.
Okay, so remark. X, B, K, L, T slash log canonical implies that the coefficients of B are less or equal to 1. Okay. Here's the proof. Suppose not. So you have some complicated divisor, and there's one of the components which has coefficients, let's say 1 plus epsilon, which is greater than 0. Epsilon can be arbitrarily small, greater than 1. But as long as it's greater than 0, I'm going to show you that we have a problem. Okay, so you pick a general codimension 2 point. So let's just pretend it's a surface. We pick an actual point on here, and we blow it up. So now we have a new exceptional divisor, E. What's the coefficient? With what coefficient does this appear? It's a smooth point on the ambient variety, so the relative canonical gives you a contribution of -1. However, we have 1 plus epsilon, so when I pull that back, I get +1 plus epsilon E, so the coefficient will be E. No contradiction so far, right? Because I would only get a contribution if I have something bigger than 1. But now I blow up this common point here. When I blow up that common point, I get a new exceptional divisor. And this one appears now with coefficient 1 plus 2 epsilon. Because this one had coefficient 1 plus epsilon. This has coefficient 1 epsilon. So I get, so I wrote down the wrong thing. I just get 2 epsilon. 1 plus epsilon is 1 plus 2 epsilon minus the relative canonical, which is 1. So I get 2 epsilon. Now I blow it up another time. So it's a slow process, but eventually you'll win. Then you'll get coefficient 3 epsilon and so on. So you get the picture. Eventually, no matter how small epsilon is, after 1 over epsilon plus 1 turns, you violate the log canonical condition.
No. But your definition was coefficient of E prime is smaller than, you didn't subtract the
I did.
transform.
I'm using this definition here.
Yeah.
So with this definition, that's how I'm computing those coefficients.
But
So the
you didn't subtract. Those E prime, the string transform B survives. So therefore? Yeah.
Here, that's the strict transform.
No, the string transform is there in E prime.
Sure.
So that survives.
So you're saying this, the way I defined it, I don't even need to go through this trouble. Okay, so you're not disagreeing, you're just saying it's more immediate. However, this argument shows you something even more interesting. It says the following. So let's let A of xb be the minimal discrepancy. So this will be the minimum of the set of all divisors E over x of the numbers A, E, X, B, right? So from the point of view, so those are sort of minus the coefficient. So from the point of view of log canonical is equivalent to saying that A, X, B is greater or equal to -1. KLT is equivalent to saying that A, X, B is strictly greater than -1. So now, my claim is that what I've just shown is that if A of X, B is less than -1, then it's equal to, then it's -infinity. Right? So here I started with something of discrepancy less than -1, so of coefficient greater than 1, and I produced something of coefficient arbitrarily big, 2 epsilon, 3 epsilon, 4 epsilon, and so on. So of arbitrary small discrepancy. So that's, if you look at the minimum of the discrepancies, it's, you know, it's either -infinity or it has to be greater or equal to -1. So this log canonical is really the threshold where you can sort of control these numbers. And in fact, you can rephrase this in terms of certain integrals not diverging. And so the log canonical threshold is the threshold for which the form corresponding to sort of the volume form of X with poles along B is integrable, is locally integrable.
I think what you have shown there is instead of giving the definition that way, you can define uniformly coefficient of B prime minus F lower star B is less than 1, bigger, less than or equal to 1, and you say for all.
Right.
So that will give you uniform definition.
So traditionally, there's several different equivalent ways of defining log canonical, and there's certain slightly nuanced differences which actually lead to slightly different notions. And I'll stick with this one so I don't make a mistake. But yeah, Matsuki just knows too much about this stuff.
Sorry.
No problem at all. Okay, so one thing maybe that one should emphasize is so suppose that X and X prime, this is birational with canonical singularities. Then they have isomorphic canonical rings. I kind of waffled about when you had two smooth varieties, they have isomorphic canonical rings, but it's true in more generality. So the point is, you take a common resolution, and now you have that the canonical class of W is the pullback of the canonical class of X plus some effective and exceptional divisor by definition of canonical singularity. Right? It's something about the coefficients being negative. So when I put them on this side, they're positive. So then the canonical ring, or maybe let's just look at H0 of multiples of KW, is isomorphic to H0 of course, multiples of the pullback of KX plus ME. But since E is effective and exceptional, by the projection formula, this is the same as H0 of MKX. And by the same exact argument, this will be isomorphic to H0 of MKX prime. So in the class of varieties with terminal singularity, canonical singularities, the canonical rings are birational invariants. And that's actually, if you think about it, the definition of canonical singularity is essentially saying that not only the canonical rings are invariant, but that statement is just, it's also holding locally over X, essentially. So it's sort of a sheaf theoretic version of the birational invariance of the plurigenera. Okay, I've talked about minimal discrepancies. done that. Just trying to catch up with my notes. I've done a lot of. Okay. Okay, maybe I wanted to make a comment about minimal log discrepancies. So minimal discrepancy, I introduced these numbers, minimal discrepancies. Where did I write it down? I had it somewhere. Sorry? I erased it, huh? Okay, so it takes a second to write it down again. So we think these numbers A, X, B, which is just a minimum of all the over E is divisor over X of the corresponding discrepancy. This is the minimal discrepancy of the pair XB. Usually we really think of a pair. You should think of these as interesting invariants that measure the singularities. So, and remember, for example, that log canonical is equivalent to A of XB greater or equal to -1. And so it's sort of not very clear that these invariants are well-behaved. It's conjecture that they're well-behaved, but not very clear. So Shokharov has some interesting conjectures about these invariants. So which ones do I want to state? So here's one conjecture. So let's look at A P X B. So this is going to be, P is a closed point. So this will be the minimum of those E's that map to P of the corresponding discrepancy. So we're looking for discrepancy over a specific point. And so there's a conjecture by Shokharov, states that APXB is a semi-continuous function. Semi-continuous of P in X. Okay, so now the question is, should it be lower semi-continuous or upper semi-continuous? Okay, well, let's think about it. Here, bigger discrepancies are better singularities. So when you specialize a point, you expect the singularity to get worse, right? So it should be APXB should drop down at special points. So, for example, when you have your elliptic curve, have a conal elliptic curve, if you take any smooth point, then APX0, it's a smooth point, so we have computed this. This is 1 for a smooth point on a surface. Just blow up a smooth point. However, we've computed at this point that this is APX0 is -1. It drops down at that special point. And in fact, the semi-continuity conjecture, I think it's known in dimension 2. So, right, so I said, I don't remember it's upper or lower. Now I figured out that it's lower.
You make a definition.
Well, you know, we could conjecture that it's one or the other, and we're not sure which. But no, of course he knows that. It has to be lower semi-continuous. So you know, that would sort of match our intuition of what we expect to happen with singularities. But even this conjecture is not known. There's even more troubling things that are not known. So, for example, another conjecture is that APXB is always lesser or equal to the dimension of X minus 1 with equal if and only if P in X is smooth and P does not belong to the boundary B, to the support of the boundary B. right? So we expect that certainly we know for a smooth point how to compute the discrepancy, and we get dimension of x minus 1. That's supposed to characterize smooth points. This conjecture is not known. It would follow from the semi-continuity conjecture. Well, not quite, but it would almost follow from the semi-continuity conjecture. In fact, question, can we show that AP xb is bounded from above by some constant, any constant, ideally dimension of x plus 1, but can one find the constant? There's no argument for that. Conjecture is true. If the semi-continuity conjecture is true, then this bound has to be dimension of x minus 1, because for a general point, it's dimension of x minus 1, and if it can only drop down, then that tells you that the maximum really is dimension of x minus 1. Okay? And there's other more daring conjectures about these numbers. So there's a conjecture known as, again due to shock growth, he's the most daring amongst us, the ACC for MLDs. It says something like, if you look at the set of all possible minimal log discrepancies, A, X, B, where dimension of X is equal to D, it's a fixed dimension D, and the coefficients of B are in some DCC sets. Let's say, for example, the set 1 minus 1 over K, where K is any integer. So this set here is ACC set. What does ACC set mean? It means no accumulation points from below. So these minimal, we didn't talk about log discrepancy, but it's the same concept. Minimal discrepancies, these discrepancies are supposed to be special numbers. They're supposed to be a well-ordered set, and they're supposed to have a lot of structure. But these conjectures are only known in low dimension, maybe 2. So these are very ambitious conjectures, and I only mention them at this point. You'll see later on why I'm interested in them, but I only mention them at this point to give you a hint that not much is known about these discrepancies. It's a very easy and convenient way to measure the singularity. They are very mysterious numbers, except in dimension 2. Any questions? You really want to ask a question. You're not sure which one. No, no problem. Yes. Well, I check what point I am in my notes. We all, no problems. Okay, so did you think about a question or?
Suppose I have a log canonical there, and when I take the log resolution, all the minimal discrepancy at each point has already shown up for one resolution.
Oh, the minimal discrepancy. So what could happen? Here's your log resolution. You have coefficient B1 here and coefficient B2 here. And the only, so the minimal discrepancy is the biggest one of these coefficients. So if we're talking about a Kelty singularity, then all of these coefficients are going to be less than 1. So in this picture, if I blow up this point, I get b1 plus b2 minus 1. I get a smaller number. So the worst has already happened. And if you have a strata which is intersection of 3 hyperplanes, it's even worse. So for the Kelty case, the answer is yes. Once you go to 1 log resolution, the minimal discrepancy has already shown up.
No, minimal discrepancy at each point has already shown up for 1 log resolution. Because it looks like...
Well, okay, so there's always some stupid reason why it's not true. So technically, if you start with this, at that point, no divisors have shown up, so there's nothing to count. You need to at least blow that point up to have a divisor that measures the minimal discrepancy at that point.
Because it looks like, if I can take 1 log resolution, and there, all the minimal log discrepancy for each point has shown up, I only have to look at the image and see how, how this point intersects with the intersection. But it looks like...
So you're doubting that the semi-continuity conjecture can possibly be as complicated as it sounds.
That's right, that's right.
Yes, unluckily there are subtleties that, that come into play. So
what's the subtlety here? Where is the difficulty for the short-proof conjecture number 1?
So,
ATXB lower semi-continuous. What's the good example where you cannot see it?
okay, so you started from something down here. Okay, so now there's a point down here whose inverse image is some nice, crazy subvariety or union of subvarieties, right? So now, so maybe now I blow up this point and I have to look at something interesting going on at the generic point of this curve. So essentially, now you have to compute the minimal log discrepancies, not just at points up here that map to that point, but also along sub-schemes that are contained in the inverse image of this point. I think that can give you something interesting. And not in low dimension, so this is not a good picture. It's in dimension greater or equal to 3 that things get interesting. Yeah. Well, I haven't worked on that conjecture. I know for a fact that people find it very hard. So if you have a great idea, I can point you to some experts in the field. Okay, so I need to say a few words about notation. I need to tell you what a non-Kelty place and a non-Kelty center is. So E is a divisor over X is a non-KLT place if AEXB is less or equal to -1, and it's a non-log canonical place if AXB is strictly less than -1. So if it's a reason why X is not log canonical, if it's a reason why X is not KLT. And V, which is just the image of E, is a non-KLT center, respectively, a non-log canonical center. Okay, so they're going to play a very important role. I should say a few words about these non-KLT, non-log canonical centers. So there's a theorem of Camerota, says the following. Suppose that X with respect to some boundary B0 is KLT. It's possible that by now you don't need this sort of extra assumption. And X with respect to a boundary B is log canonical. Then if V1 and V2 are non-KLT centers. Right, so non-KLT centers, remember that it means the discrepancy, the image of something of discrepancy -1, so of coefficient actually equal to 1. Non-KLT centers. Then every component of V1 intersect V2 is a non-KLT center. And in particular, you can talk about minimal non-KLT centers, right? Because whenever you have two non-KLT centers, every component of the intersection is a non-KLT center. So you can just keep intersecting until you get a minimal one. So does the statement make sense? So, you know, I'm not going to prove this. It's a consequence.
Sorry,
yeah.
B0 and B. B0 and B.
OK, B0 is an auxiliary divisor. B0 is an auxiliary divisor. It's saying the ambient space, say that x is q factorial, put B0 equals to 0. The ambient space is KLT. When I add a boundary, it becomes log canonical. Then, when I look at non-KLT centers, then every time you have two of them and you intersect them, you get a new non-KLT center.
Since that, if we don't have to assume that B0 is KLT, I thought XP is LT, LC is not.
So it's quite possible that there's a result of Fujino-Gongyo that says exactly that. So it's quite possible. I suspect that this is not necessary. The version that I was looking at had that hypothesis. Kawamata's original theorem has that hypothesis. But since then, the subject has moved forward. So Kawamata's theorem is probably 20 years old. And, so I suspect that in this version, it might be due to Fujino-Gongyo. Yeah, so if you don't like this condition, you can ignore it. So why would you expect something like this to be true? So what's going on? Here's your x, and you have two log canonical centers, V1 and V2, right? And you want their intersection also to be a log canonical center. Okay, so you look at a non-KLT center. You look at the log resolution x prime, and what you notice is that you have a divisor E1, which has coefficient 1, which is mapping down to V2, okay, let's call this E2, which maps down to V2. And you have another divisor, E2, also of coefficient 1, E1, mapping down to V1. And you're looking for a divisor of coefficient 1 that maps down to the intersection of these two centers. Okay, so there's something wrong with my picture, right? Because in my picture, there's no such divisor. What's going on? So we're looking for a divisor here with coefficient 1, which is mapping down to the intersection. So what's going on is essentially some version of the connectedness lemma. The set of non-Kawamata log terminal places is connected. So whenever you have one place that maps to V2 and one place that maps to V1, since they have to be connected, either these two intersect, or there's some divisor of coefficient 1 that's sort of connecting them. And that's what's going to give rise to this log canonical center. So, so here's another picture when you have a node in C2. When you blow it up, you get your exceptional divisor. And now you've resolved the node. And this exceptional divisor appears with coefficient 1. Right? So, and we know that that has to happen by this connectedness of the non-KLT places, because otherwise I would have a non-KLT place here and a non-KLT place here, and they wouldn't be connected in the fiber. So maybe next time I will prove that result. Let me just state a couple more things about these non-KLT centers that are very useful, so one starts believing that they're going to play a central role in many of the proofs. And then next time I will actually start honestly talking about the minimal model program, how to run the minimal model program, and things like the cone theorem and the base point free theorem. So Yes.
But you need more unconnectedness, right? Because
Yes, of course. It's not just a consequence. I'm just saying what is some intuition behind why it has to hold.
Because it might be connected, which
It might be connected by something big that creates another log canonical center through the point, but not actually the point itself.
dominating.
Yes, yes. So there is a little bit of work to do, and you probably want to localize at the generic point of one of the components of the intersection, so you know you won't miss it. And you have to be a little bit careful. In spirit, it's very close to the proof of the connectedness lemma. In practice, you have to be a little bit more careful.
In your proof, do you assume this auxiliary thing?
So first of all, it's Kawamata. The proof that I'm familiar with is Kawamata's proof, and he definitely assumes that. But it's not necessary anymore. I will not do the proof of that. I might do the proof of the connectedness lemma, which has a similar flavor. So let me mention another theorem of Kawamata. Let V be minimal non-Kelty center of a log canonical pair XB, and let's let A be an ample divisor. Then I can compare Kx plus B plus, I throw in epsilon times the ample divisor for good luck, restricted to V, and this, I can write it as K of V plus B epsilon V, where V, B, epsilon V is KLT. So in particular, V is normal. So what this is saying is that you can very effectively relate the geometry of the ambient variety and the geometry of a minimal non-Kawamata log terminal center. And so this can be exploited, for example, in trying to prove the base point free theorem. So sort of in the base point free theorem, you have some little a bigness of a certain divisor is built in, so you can sort of play around with a little bit of an ample divisor. And V arises essentially as your base locus. So if you can prove that this gadget does not have any sections, maybe you can lift those sections to the ambient variety and derive a contradiction.
I'm sorry, Chris. I don't
Yes.
understand
The statement. Okay, so
for all ample, epsilon is
right. So you don't really need an epsilon. You could just say for any ample Q divisor, this formula will hold, but then this B will depend on the ample divisor. Or you could say fix one ample divisor, then for any epsilon greater than 0, I forgot to say for every epsilon greater than 0. Maybe that's what's a bit confusing. So you put more ample divisor. I don't think that people have gotten rid of this condition yet, but I have to look at the literature to make. I mean, ideally, you don't like to have to put that in the picture as well. I don't think that's been gotten rid of yet, except maybe in certain situations. But yeah, so think of it as a fixed ample divisor and epsilon being arbitrarily small. But if you prefer, you could just replace this by arbitrary ample divisor. It always works.
small for any.
Yes, for every epsilon greater than 0, this formula holds.
So for choice of expression of A as a field divisor?
Mm-hmm. Yeah, so, okay, so technically I should say this is Q linear equivalent to, because we will make a choice of the divisor BV. We only know, so technical result is that you can write it as a pair plus a Neff divisor on some higher model, and then you use the ampleness to perturb the Neff divisor into actually an actual Kelty pair. Okay, so look, it was supposed to do 2 hours, correct? This is a good time to stop. Okay, perfect. Okay. So next time I promise to get into the actual details of running the minimal model program and try to begin doing some of the harder work.